Hi, welcome to the third of our review lectures before we really get into the subject of electromagnetics for engineers. Today we're going to cover in a very short period of time a quick review on algebra for scalars. And remember, scalar numbers are numbers that have sort of a value. They don't have a direction, they don't have dimensions to them like vectors, which we'll cover later. And these rules really only apply to scalars. So we have to keep these two types of numbers separate when we're working on electromagnetics or we get into a lot of trouble. And so, really, this is something you should already know. There's some basic rules of algebra. They can be written down here. It looks like there's something like 11 of them, and so they're not that hard to memorize. You probably don't have to memorize them. You probably know how to do all of this stuff already from taking courses in high school and in early college. But here they are in case you need to know them. One of the important things to remember, though, about algebra is these letters, which as you know are called variables, don't have to be A and B. I can rewrite the basic rules of algebra independent of the types of signals. So, for example, if I call A x squared plus 3x and I call B negative 7, then I can rewrite this rule like this, and it works. No matter what group or symbols you put in here, or even numbers. For example, here I'm replacing A with 2. These rules hold all the time. And so if you're not aware of these, memorize them, because without these it's really hard to do the tricks you need to manipulate equations, as you'll come across in your electromagnetics fields course, to try to get answers the way your instructor often likes them. Another thing that's very important to remember in algebra is this guy. This is the equal sign, and it's really surprising what this equal sign represents and how many people really don't grasp the power of it. So if I write something like, say, A equals B, what this means is, in mathematical terms, A is B. There is no difference at all between them. In the real world, they may represent two very different things, but in mathematics, anything connected by the equal sign is absolutely identical. So, for example, you can do kind of ridiculous things here, like write cow equals fish. Now, we know cows are not fish in the real world, and so one would tend to reject this equation if you came across it. However, in mathematical terms, the variable cow is being stated as being equal to the variable fish. Cow and fish can represent anything. Remember, the names don't matter. It's the manipulations of the symbols that are important in mathematics. And this equal sign says the symbols on either side are exactly the same. And it doesn't matter if you have a long series of equations connected by equal signs. Anything from the first equation is equal to something in the 10th equation if you go and do these types of manipulations, and can be substituted in there. And this is a very powerful thing and allows a huge number of tricks to be done in mathematics. Another thing in our review of algebra is to understand logarithms. Remember, we often have in algebra a number raised to some power. Here we're saying x is equal to a, whatever a represents, raised to the y power. Now, if we want to calculate what y is, and we want to do this equation and we reverse, we use a logarithm, which is right here. And the way we would say this is y is equal to the log base a of x. And typically a is either equal to 10, base 10 logarithms, or a is equal to e in this equation. Remember, and this is 2.7 something something something. You can look it up if you need it. And these are typically written as log, and if you see log without that number a down beneath it right here, then you can assume a is equal to 10. And if we have log base e, we call it a natural logarithm, and we write it like this in many cases, except some computer programs don't do this, so it gets a little bit confusing. Logarithms are really useful for a lot of reasons, and so you should remember these things about multiplication of logarithms, division of logarithms, and logarithms raised to the power as algebra rules you should probably commit to memory. One of the things that logarithms are really useful for is plotting numbers of very, very different scales. And remember, we talked about in one of the previous review videos that the range of numbers that we're going to sort of get to range from 10 to the minus 12 up to like 10 to the 12th or 10 to the 15th, a huge range of physical numbers. And so let's take a simple example of that. Let's say I plot the value of x squared on the range of 0 to 100. Well, this is pretty easy. At 0, x squared is equal to 0, but out here at 100, x squared is equal to 10,000. What if I want to plot x squared and x to the 4th on the same graph? Well, at 0, they overlap. They're exactly the same point. So let me actually grab a blue color here so that I can draw the blue line. However, at 100, where x is equal to 100 out here, x to the 4th is equal to basically 10 to the 8th, 10 times 10 to the 7th. However, x squared is going to be equal to 10,000, or 10,000 times less than that. So it would be a tiny little point down here that you couldn't even see. And if you plotted these two graphs on top of one another, you'd get a green line that went up like that and a blue line that went basically flat, and you wouldn't be able to see it at all. This gets even worse, essentially, if you want to go and plot something like 2 to the x, which raises to a power of 15 times 10 to the 29th when x is equal to 100. And so these things are not at all comparable if you want to see them on the same graph. Now, these graphs are linear graphs, and this is an important distinction. Every time we jump up in units, say from 0 to 5,000 to 10,000, each next unit is an addition. So this is 0. To get to the next unit, we add 5,000. To get to the next unit, we add another 5,000. And we can come in, we don't have to go as 5,000s, we can go as 1s and 10s or any number. For example, here, we're essentially, every step is 5 times 10 to the 7th. The next step is an additional plus 5 times 10 to the 7th, and so on and so forth. If you plot these on a logarithmic scale, and remember I've been going on for a while here, so remember we're talking about logarithms, you can see that the 2 to the power x on a logarithmic scale and the x squared, which is the blue line on the logarithmic scale, and so on and so forth, really can be seen very clearly on the same scale. Because here what we're doing is we're jumping by steps that multiply by 10. So we go from 1 to 10 to 100. And so the lowest value we have is 1, and we take that and we multiply it by 10 to get 10. We multiply 10 by 10 to get 100. The same here. We're starting with 1 and we're multiplying it by 10 to the 20th. To get this unit, we multiply the next increment or scale on our graph by 10 to the 20th, and they don't have to be 10 to the 20th. They can be any number. The key difference is linear scales add. Log scales, to jump from unit to unit, the scales multiply. So these are our two simple arithmetic sort of manipulations we do, but we just apply them to the graph to get the units. And that's the difference between logarithmic and linear graphs. And if you're plotting a big range of numbers, it's really important to use that logarithmic graph, the log scale. Let's go ahead and clear the screen so we have some space to work with. It turns out the fact that the logarithmic scales multiply things are really useful in engineering. And we've developed a system of units we'll get to in a minute called decibels. But in order to see why this multiplication is useful and plotting things on scales that multiply are useful, let's look at two sort of different attenuators, so things that are going to drop the power down. So if we have power in coming in here, into the first system, we're going to get 1% of the power out. So we'll say P right there. And then our second system drops the power by an additional 10% to measure P out right there. So if essentially we have the power coming in of 1 right here, at this point we're going to have a power of 0.01 because it's only 1% of what comes in. And here we're going to have a power of 0.001 because this 0.01, 10% of that comes out. And so you can see that when you have two systems that cascade, the total power is 1% times 10%, which is 0.1%, or equal to 10 to the minus 3. And so the fact that systems cascade together, not by adding but by multiplying, is why these logarithmic scales are really useful in engineering. Now it turns out that they're so useful that engineers developed a scale called decibels for that. And a decibel is defined to be right here. It's defined in terms of power. This is important. The units of decibels are defined for power, and it turns out that we can calculate the decibel gain or loss from a system by taking the power out, dividing it by the power in, taking the base 10 logarithm of that, and then multiplying it by 10. So for our case, the power out is 0.001. The power in is 1. This is obvious. This is 10 to the minus 3. Log base 10 of that is minus 3. 10 times that is minus 30. So this system cascaded together has a loss of minus 30 decibels. This one, of course, has minus 20. This one has minus 10. So instead of having to multiply, notice we just add those two numbers. And that's why engineers like decibels, because they turn multiplication problems into addition problems. This is not a big deal these days because we have electronic calculators. But back in the days when engineers relied on slide rules, this was a system, the decibel system, that allowed much simpler and more accurate calculations. It turns out that you can also calculate the decibels for amplitude, not power. And this is just done by a little bit of math. We recognize generally that the square of the amplitude is equal to the power with some ratio that generally divides out. And so if we essentially can approximate our power output as 1/2 the voltage output, these 1/2s are going to cancel out of the equation. So we get V squared out divided by V squared in. Remember, with this law of logarithms right here, we can take this 2 and move it to the front and turn that 10 into 20. And so this is the equation you use to calculate decibels if you have amplitudes rather than powers coming in. And so that's the end of algebra review. Let me remind you of a really cool site online called the Khan Academy that has hundreds and hundreds of really short videos on topics similar to these. And if you didn't understand this or need a more simple review or want to explore topics further, that's a great place to go to find videos.